In the previous class, we covered in detail the contents of the course and evaluation scheme. We also covered the basic breakdown of the lectures. Today, we will cover review of basic concepts. We will just try to recapitulate some of the essential concepts which you have already studied in your undergraduate education. After we finish this review, we will begin the first important topic of the course, that is the direct stiffness approach for computer applications. We have studied that the methods of analysis for structures can be broken down into two categories: force methods, where forces are the main unknowns, and displacement methods, where displacements are the main unknowns. If we list the analysis methods which we have studied in our undergraduate curriculum, the method of consistent deformations is a force method. Similarly, slope deflection method, matrix stiffness method, direct stiffness method for computer applications, and the moment distribution method, they are displacement methods. Before we begin analyzing a structure, we have to make sure that the structure is stable. Then if we are using the force method, the next question comes is the determinacy, whether the structure is determinate or indeterminate. If the structure is indeterminate, we need to work out the degree of static indeterminacy. Similarly, in the displacement method, we need to work out the degree of kinematic indeterminacy. Let us review these aspects. Let us study the stability and determinacy aspects, especially with regard to the necessary and sufficient conditions. If we have a 2D structure, then to be stable, it must have at least 3 reactions. The requirement of 3 reactions stems from the fact that the structure must satisfy equilibrium of forces in the x direction, equilibrium of forces in the y direction, and the moment equilibrium about the z axis. In addition to this minimum number of reactions, the structure should not suffer from any kind of geometric instability. For a 3D structure, the minimum number of reactions is 6, because the structure must satisfy now 3 force equilibrium conditions along x, y and z axis, and 3 moment equilibrium conditions along the 3 axes. In addition, the structure should not have any geometric instability. In force method, before we begin analyzing a structure, we must work out the degree of static indeterminacy, in short DSI. What is DSI? DSI is the number of unknown forces over and above the minimum required to satisfy the conditions of equilibrium and stability for the structure. For example, if we consider a 2D beam with simply supported conditions at the two ends, then what we find that there are 4 reactions. One reaction is thus extra, so one of the supports can be turned into a roller support. So in this way, the degree of static indeterminacy, or DSI, is 1 because the structure is carrying 1 extra reaction. So for 2D beams, we can frame mathematical rules. If we denote the number of reactions by R and the conditions of construction such as an internal hinge as C, then we can frame following rules. If R is less than C plus 3, then the structure will be statically unstable because it does not have sufficient number of reactions. If R is just equal to C plus 3, then the structure would be statically determinate provided it does not have any geometric instability. On the other hand, if R is greater than C plus 3, then the structure would be statically indeterminate provided again it suffers no geometric instability. If we see these rules in a deeper sense, we would find that basically it is the trade-off between the number of unknowns and the number of equations. In the case of statically unstable structures, we find that the number of reactions or the unknowns, they are less than the number of available equations, which are C plus 3. 3 equations come from the equilibrium and C comes from the conditions of construction. So because the number of unknowns are less than the equations available, so such a system does not have any solution. On the other hand, if the two sides are equal, that is R is equal to C plus 3, then there is a unique solution and the structure is determinate. Finally, when R is greater than C plus 3, then the system of equations is such that it has infinite solutions. So we have to pick a solution which satisfies the compatibility conditions. So that's why here the structure is indeterminate in nature. Let us consider an example structure. So here we have a beam with an internal arrangement, a condition of construction such that there are two levels and both levels of beams, they are connected by a simple link. A link element cannot resist any bending moment and is only a two-force element. To take a decision on the stability and determinacy of the structure, and if it's indeterminate, we need to find the DSI. So the first step is that we do a comparison between R and C plus 3. So here, what is R? So what we find, the total number of reactions are 3. Now come to the point of C. So think of how many conditions of construction are there in the structure. I give you 30 seconds to think about. So here let me tell the answer. You also must have thought something, because here we have a link element connecting the two beams, the left hand beam and the right hand beam. So at the link point there are two conditions of construction. One, this connection cannot transmit any bending moment from one part to other. Secondly, the link is a two-force element, therefore it cannot resist any force perpendicular to the link. Hence, there cannot be any transfer of axial force from one part of the structure to the other. So the C comes out to be 2 here. Now, if we substitute the values of these terms, then we find that the left hand side R is 3 and right hand side that becomes 5. So here the number of reactions, they are less than the minimum required to ensure stability. Or in other words, the supports are inadequate. Hence, the structure is unstable. This decision we have arrived at by mathematically computing. But even without mathematical computations, just by simple inspection also, we can arrive at the conclusion that the structure is unstable. Just imagine applying a horizontal force at the roller support on the right end of the structure. What will you find? The link will undergo rotation and the structure will collapse. Hence, the structure in the current situation is unstable. Let us consider another example. So here we have a beam with pin supports at both ends, and it also has an internal hinge. Let's do here the computation of the key parameters, that is R on one hand and 3 plus C on the other. So here we have total of 4 reactions. So R is 4. The value of C, that is condition of construction, is 1 because it has one internal hinge. So this gives rise to the condition that at the point of the hinge bending moment is 0. So what we find that both the terms are equal, so R is just equal to 3 plus C. So computation shows that the structure is determinate. Do you think so? So just take a brief pause and think about whether there is any kind of geometrical instability or not. Hope you have thought over. Let's come back and visualize. If we apply a force at the point of the internal hinge vertically downwards, what will happen? Because of the presence of the internal hinge, each of the two elements behave like link elements. Therefore, the elements cannot resist any force normal to themselves. So, the effect of application of this force is that both members shall undergo large rotation about their respective hinges, that are the two end supports. So this will lead to a very large inelastic displacement, and this is considered as unstable structure. So here what we find that the number of reactions are adequate because the equality R equal to 3 plus C is being satisfied, but still the structure is unstable. So why it is unstable? It's unstable because of the internal hinge. Inadequate arrangement is not there, but there is an instability within the structure. So this is called as internal geometrical instability. It may also be noted that here the structure will not undergo total collapse. It will undergo large inelastic deformation, which is unacceptable from structural engineering point of view and considered as instability. Let us consider another example. So here we have a structure with multiple supports and there are two internal hinges. So if we compute here the parameters R and C, R very easily comes out to be 6. There are 6 reactions, and C is definitely 2 because of the two internal hinges. What we find that the two terms R is 6 and the term 3 plus C comes out to be 5. Here R is greater than 3 plus C. So the computations show it is an indeterminate structure. However, before jumping to a final conclusion, we must check if there is any indication of a geometric instability. No, we don't find any reason for any kind of geometrical instability. To check yourself, just isolate the left part of the structure, and if we see in itself, it's stable. Similarly, the right hand side of the structure is also stable in itself. So if the two are stable, then definitely if a connection is made between the two, the new structure will also be stable. Hence, the final conclusion is that the structure is stable and indeterminate to first degree. Let us now formulate the mathematical rules for stability and determinacy of truss. We have to see what are the unknowns and what are the number of equations. In our truss, the unknowns are the axial forces in all members and the external reactions. So that is, if we denote the number of members or bars as B, then the total number of unknowns will be B plus R. Coming to the equations available, at each joint in a 2D truss, there are two equations of equilibrium. Summation Fx is 0 and summation Fy is 0. So if the total number of joints in the truss is j, then the total number of equations available is 2j. So now we can frame the rules. If b plus r is less than 2j, then definitely the truss will be unstable because the system of equations does not have any solution. On the other hand, if b plus r is equal to 2j, then the truss will be statically determinate provided there is no indication of any geometric instability. Finally, if b plus r is greater than 2j, that is, the system of equations has infinite solutions and we have to adopt a solution which satisfies compatibility conditions, then we come to conclusion that the structure here, the truss, is statically indeterminate provided there is no geometric instability. So it's very important here also to inspect the structure from point of view of geometric instability. Someone may now ask question that we have not considered the equation for overall moment equilibrium, that is summation mz equal to 0. Should that not be an additional equation? The answer is no. We have already considered the force equilibrium of all the joints. So by suitable linear combination of these equations, we can obtain the equation for the overall moment equilibrium of the structure. Hence, it is not an independent condition. Let us see an example of a truss. So here we have this truss with supports one pin and other roller. So if we now compute the two terms b plus r and 2j, we find that b plus r comes out to be 11. You can count yourself the total number of bars, and j is 5 here, so 2j comes out to be 10. So what is our observation? Our observation is that the left hand side is greater than the right. Now we need to ascertain that there is no geometric instability. Yes, inspection says that there is no indication of any kind of geometric instability. So we can conclude that here the structure is stable and indeterminate to first degree. Next, if I ask you a question, can you convert the structure into a determinate structure? The answer is yes. The structure has additional one member over and above the numbers necessary to make it a determinate structure. So if we remove a member such that the truss action is not disturbed, then it converts into a stable and determinate structure. There are multiple ways of doing that. Next, I have modified the previous example structure. The two top inclined members, they are made horizontal. Now if you do the computation, b plus r comes out to be 7 plus 4, that is 11, and 2j comes out to be 10. Before jumping to the final conclusion based on the numbers, we must inspect it very carefully and look for any sign of any kind of geometrical instability. So if we do that, we'll find that the top portion of the structure has a hinge. So if we apply any load at the midpoint, structure will undergo a large inelastic deformation locally because of the rotation of the two members about their respective left and right hinges. Hence, the structure has internal geometrical instability. So the final conclusion is that the structure is unstable. You can rework the same example by converting the right support into a roller. In that case, you will find both b plus r and 2j, they are equal, apparently giving a notion that the structure is determinate. However, it will be again unstable for the same reasons which are explained just now. Let us now frame the rules for stability and determinacy for the case of rigid frames. In a rigid frame, there are three unknown forces in each member: the axial force, shear force, and the bending moment. So the total number of unknowns in the structure will be 3b plus r. Coming to the equations, each joint has three equilibrium equations the summation of all the forces in the x direction is 0, the summation of all the forces in the y direction is 0, and the moment equilibrium about the z axis. So here the total number of equations will be 3j plus c. So based on these, we can frame the rules that if 3b plus r is less than 3j plus c, the structure will be statically unstable. On the other hand, if the two are equal, then the structure will be statically determinate provided there is no geometric instability. Finally, if 3b plus r is greater than 3j plus c, the structure will be statically indeterminate provided there is no geometrical instability. Just like for the case of the truss, here also the equation for overall moment equilibrium about the z-axis is not an independent, and it results from the 3j equations for the joints already considered. Let us see the example of the two-story frame. So here the total number of members is 6. The number of reactions are 6, 3 at each support. The total number of joints is also 6. So if we do the computation, here 3b plus r comes out to be 24 and 3j plus c 18. Visual inspection shows that there is no evidence of any kind of geometric instability. So we can very easily come to the conclusion that the structure is stable and indeterminate to 6th degree. Let us consider the same two-story frame with one difference, that there is a hinge at joint P. Now when we compare the terms 3b plus r and 3j plus c, b, r and j remain same. So what changes is c, the conditions of construction. So any guess how many independent conditions of construction are there? If we look closely, the conditions of construction C are 2, and they are that there are 3 members meeting at the joint. The bending moment in any 2 of the members to be 0, that is an independent condition. So we say that MBC and MBA both are 0. Then the third member, that is BE, will automatically have 0 moment because we have the moment equation already considered in 3j equations. So just 2 of the moments, they are forming the sufficient conditions for construction. So C is 2. Now when we input these values, the difference between the two terms is 4. So then the next question comes, if there is any sign of geometric instability? No, there is no reason for any geometric instability. Hence, we come to conclusion that the structure is stable and indeterminate to 4th degree. We have a final set of exercise for you. I am just holding this slide for say 30 seconds, and on paper and pen try to work out the degree of static indeterminacy for the structures shown here. The determination of the DSI is the first step if we want to use the force method of analysis. So the first structure, where we have a beam under UDL with fixed end supports at both the ends. If you work out the degree of static indeterminacy using the method learned, you will come out with the number 3. However, now by observation of the conditions of symmetry and taking into account the fact that in beams there is no axial force, we can further bring it down. The horizontal reactions at the supports, they are 0. Similarly, the values of the vertical reactions can be determined based on the symmetry and from the vertical equilibrium that both the vertical reactions shall be equal to WL by 2. Then, making use of the symmetry, the two unknown moments, they will be equal and opposite. So the degree of indeterminacy reduces to 1. Next is a truss. So if you just do the computation, the answer should be 0. Then we have a frame where you do the computation, the answer comes out to be 6. And then we have a beam again with internal conditions of construction. So this particular beam has 3 internal conditions of construction which can be identified very easily, 1, 2 and 3. So at the first hinge, moment is 0. At the second location where there is a vertical link element connecting the two substructures, there are 2 conditions, that is no bending moment can transfer and no axial force can transfer. So if you input here the values, the answer comes out to be 0, and then you inspect whether the structure has any case of geometrical instability. So if you inspect it properly, you will find that there is no such case, hence the structure is stable and determinate. In force method, basically forces are the unknowns. If the structure is determinate, we just have to apply the conditions of equilibrium, work out the equations and solve them, and answer is with us. In case the structure is indeterminate, then we have to choose redundants. Then we form compatibility and equilibrium equations both. After solving the equilibrium and the compatibility equations, we get our answer. So in addition to equilibrium equations, we have to form compatibility equations also. We just take the example of a beam under UDL with fixed conditions at both the ends. So the first step is that we convert the structure into a primary structure, which means removing the extra reaction or force and converting the structure into a stable determinate structure. The primary structure is now assumed to be under the action of the loads. We solve the two systems independently and then apply the compatibility conditions. For example, here the compatibility condition is that the rotation θ1 is equal to the rotation θ2. θ1 is the rotation of the primary structure under the action of the UDL, and θ2 is the rotation in the opposite direction under the action of the redundants. The application of the compatibility condition θ1 equal to θ2 enables the determination of the redundant x. Then the other unknown reactions can be obtained simply by equilibrium conditions. So you are very much familiar with this method, the method of consistent deformations. After the review of the force method, let us briefly review the displacement approach also. In the displacement method, basically displacements are the main unknowns. Here we work out the degree of kinematic indeterminacy or DKI. So what is DKI? DKI is the number of independent displacements possessed by the structure. If we know these particular displacements can be computed at any other point of the structure. Another common term for DKI is degrees of freedom. Let us consider trusses for DKI. If we are dealing with a plain truss, then DKI shall be equal to 2j minus r, where j is the number of joints and r the number of reactions. This formula is very obvious because at each joint there are two possible displacements, one along the x-axis and the other along the y-axis. For the particular truss shown here, by this calculation the DKI comes out to be 5 because there are 4 joints and 3 reactions. Now the next job is we need to identify them So all these 5 independent displacements can be very easily identified as shown here. Similarly, for a plane frame, the expression for dki is 3j minus r. Why 3 comes here? Because there are 3 independent displacements at each joint. One translation in the x direction, other in the y direction, and then a rotation. Now for the example shown here, where there are 4 joints and 6 reactions, the answer comes out to be 6, and all these 6 independent displacements can be identified as shown here. Let us bring here some complication. Let us consider 2D frames with all members inextensible. Then we will have another term, that is Ci, which is the number of conditions of inextensibility. It is generally equal to the number of inextensible members. However, in certain cases this may not be true. So the presence of inextensible members basically lowers the dki value of the frame. So for this particular frame, because there are in total 3 members, the dki comes out to be 3. So what happens is that because of the inextensibility of members, the 2 vertical translations, they are not there. Then in the horizontal direction also, because the 2 columns are connected by an inextensible beam, the 2 translations at the 2 top joints, they are same. Hence the dki is 3, and the 3 independent displacements are basically 2 rotations at the 2 top joints and 1 common horizontal translation of the top floor. Let us now bring here another complication, that is releases. Release means an internal hinge. So what happens because of the release? The degrees of freedom increase. So for a plane frame, the expression for dki becomes 3j minus r minus ci plus f, where f is the number of releases. Basically f is equal to the additional rotations produced on account of the hinges. At a particular joint, if there is a hinge, then f is equal to n minus 1, where n is the number of members meeting at the joint. So for this particular frame, we find that because there are 2 members meeting at the hinge, the value of f is 1. So the final answer for the dki comes out to be 4. And we can identify these degrees of freedom as shown here, 1, 2, 3 and 4. So at the right top joint, there are 2 independent rotations, because now the joint is not a rigid joint. For a space frame, the expression can be extended very easily. Only thing is that 3 has to be replaced by 6. At each joint, there are 3 translations and 3 rotations. Hence, the equation becomes 6j minus r minus ci plus f. Let us consider an example. For this particular plane frame with inextensible members, the number of releases is 2. The final answer for the dki comes out to be 8. You can do this exercise yourself. And now we are finally identifying these independent displacements as shown here. 1, 2, 3, 4, 5, 6, 7, 8. So out of these, 6 are rotations and 2 are translations. Now consider the same frame as in the previous example, but here the hinge is different. Now if you look closely, the hinge is in the beam only, whereas the column is continuous. So in this particular case, f will not be equal to 2, but f will be equal to 1. That is, there is only 1 additional rotation on account of the releases, and that is an additional rotation in the beam. So if we look at the particular joint where this particular beam is meeting, then there is 1 rotation representative of the beam and the other is for the joint consisting of the two column members. So you can yourself work out the final answer, which will be 7 in this particular case. Now, how do we find f when the particular frame is a space frame? In a space frame, if there is a common hinge at a joint where members from 3 directions are meeting, then f will be equal to 3n minus 3. This is because each member will have now 3 independent rotations. 3 has to be subtracted because this number has already been considered in overall for the joint. You can convince yourself on this matter. So thank you very much. For queries and for live discussion, just join our MS Team channel and we'll have some other discussion and question answer sessions over there.